Welcome to today's video. Today I'm going to talk about flow resistivity and the different approaches in terms of using different acoustic materials, taking into account their absorption characteristics. So I'm using a website, it's called acousticmodeling.com. I'm going to put the link in the description. You can do different kinds of approaches in this website with different configurations. So I'm just going to start with just one very basic prediction, which is a panel of 50 millimeters. And what we have here on this chart is different materials with different flow resistivity values. So for instance, this blue line over here has 40K, the green line 20, and this one, the red 10K, and the orange one 5K. So how do I relate this to the different materials? You probably need to check your local supplier or manufacturer for further information. I'm going also to place a website on the link description called bobgoats.com, which has a section with different manufacturers and the density for different materials, but also the flow resistivity, which is the most important value for acoustical absorption prediction. And so as I was saying, usually the higher the flow resistivity, the higher the density of the material. But that is not only true, so we need to be aware of that. So one thing is density, another thing is flow resistivity. So there's tons of misconceptions about this matter. The first one is that high density materials are better for sound absorption, and that's usually quite incorrect. Usually it's the less denser materials that have the best absorption curves. Then there's also the misconception that there's a direct link between density and flow resistivity. And for instance, we would consider that, okay, we are going to decrease the density of the material, and the flow resistivity is also going to decrease, and the absorption is going to increase. And that is not always correct, because different materials have different holes that perform this kind of sound absorption. For instance, one thing is rock wool, another thing is acoustical foam, and another thing is PET panels. They all have different inner structures, and they absorb sound in different ways. Actually, the process of absorbing sound is the same, which is transforming kinetic energy into heat loss. But the materials, they react to the sound in differently. So as I was saying, and not to go very further into this discussion, the blue line is the denser material. So this would probably be mid-density rock wool. The green line would be light density rock wool, or probably an acoustical foam. And then the two other curves would be PET materials with different flow resistivity. And when we look at this chart, we can see different, we can extract different information. So for instance, we can see that the material with higher flow resistivity for this type of configuration actually underperforms the other materials for mid and high frequencies. But in terms of the range of the frequencies that the panel is able to absorb, this is actually the best option. For instance, let's say that I usually use 0.66 as a good starting point, and if we draw a line over here, we can see that for 5K rails, the frequency that we have here is 900 hertz. The red line is 500. The green line is the red line is 600. The green line it's around 500, and the blue line is actually 300. Okay, so this depends on what type of room are we dealing with. We want a panel that is more effective at mid and high frequencies. Then I would probably choose acoustical foam or a PET. Now, if I'm dealing with something that I want more control over the mid frequencies, then probably I would choose the mid density rock wool panel, something like 70 kilograms per 70 kilograms per square meter. Okay. Now, if I change the thickness of the material, or if I start adding an air cavity behind the material, this is going to change completely. So what I'm going to do now, I'm going to change the parameters, and now I'm going to increase the thickness of the panel, and we're going to see if this curve is going to change a lot or not. So I'm going to go here, amend materials, and now I'm going to increase this. So now I'm putting 100 millimeters instead of 50 millimeters or 10 centimeters, and I'm going to calculate. And now, so the configuration has changed quite drastically, because the difference, for instance, from the panel with higher flow resistivity really drastically underperforms compared to the other panels at mid and high frequencies. And then this distance over here actually is shortened from this point over here. So now, for instance, my panel with high density at 0.6 absorption coefficient, we have a frequency of around 100 and I don't know, 120 perhaps. But the green line we have 180, and the red line we have 210. So this difference is actually becoming less evident. And then perhaps on this case, probably probably I wouldn't pick this material to use. I probably use this material over here. So maybe 30 kilograms per square meter of rock wool or an acoustical foam. Okay, instead of the high density. Now let's increase this to a larger thickness. Let's assume that we want a very thick panel, and that we are treating an acoustical studio, for instance. So we are treating the first reflection points of a recording studio. A recording studio, and we're going to increase this to 20 centimeters. Okay, same approach, and then when we calculate, now this drastically changes. I'm going to do one thing. Let me change here the prediction module. This one. Okay. So in this case, we actually see that for panels with great thickness, the material with high density or with high flow resistivity is actually the worst material to use. And then we will probably choose, I don't know, I'll probably choose this one, the path with 10K rows to treat my studio if I want to use a very big, a very thick panel. So as you can see, this is not pretty straightforward. We need to do lots of modeling and lots of testing if we are using custom panels. And then, for instance, I have a spreadsheet with I don't know, thousands of measurements from different labs. So sometimes I also like to compare this prediction with predictions that have been measured in an acoustical certified laboratory, just to make sure that things are similar or approximate. Now we are going to change the. Now we are going to change this, and I'm going to place an air cavity behind the panel. Okay, and now we're going back to our first panel with 50 millimeters, and we're going to add 50 millimeters of air cavity behind. So this is going to increase the performance of the panel when compared to a panel without air cavity behind. 50-50, okay, this is correct. Okay, let me go back to Komatsu. Okay, calculate. Okay, so now we can see that the performance of the panels on this area has been increased because we have actually placed the air cavity behind. And for instance, this region over here was over here in our initial model. This point over here was almost 1000 hertz, and now because of the air cavity behind, it's 400 hertz. So as you can see, placing an air cavity behind the panel actually has great impact over this region over here, over having extra efficiency at low mid frequencies, starting, for instance, from 100 to 500 hertz. And as you can see, the panel has the difference between the panels has decreased over this area. So I will probably, in this case, I don't know, for typical practical solutions, probably I would choose the green line. Now, we can actually go backwards, and now we could probably increase, let's say that we have space in our room, and then we actually place an higher air cavity behind the panel. So this is a good trick to have extra absorption. So when you do this, so this is basically this area over here has shift to the left, and so we have increased absorption over this area over here. So it's not very different from the last panel. Now I want to do something different. So to finish our video, I'm going to maybe choose one specific flow resistivity. So let's say I'm going to put, I don't know, let's assume 10K, okay? So we're going to, and then we do like this, copy. So I'm going to, what I'm going to do is basically keep the same flow resistivity and the same thickness of the panel. I'm going to decrease, I'm not going to erase here the legends because they're not necessary. So what I'm doing now, I'm going to keep the same thickness, but I'm increasing the air cavity behind, and for the same flow resistivity. If we hit calculate, oh, sorry, I need to do this, not use. Let me change the prediction to, okay, maybe it's straightforward. not working. Okay, sorry, I need to, sometimes the website has some problems and it doesn't work correctly, so I need to do this all over again. So 50 millimeters, 10,000 for flow resistivity, no airbag, copy, air absorption 50. Let me do 4 absorbers too. Okay. Okay, so now we have our chart over here. And now we see just huge differences for having the same material and changing just the absorption behind. And changing the air cavity behind the panel. As you can see, the difference is quite straightforward. Like I said, I like to use this 0.6 as a reference, and 0.6 with no air cavity behind. We have a frequency of 600 hertz, and if we placed 10 centimeters behind, which is the red line, we have 200 hertz. So that's a huge difference in terms of absorption over this area. Now let's compare. Let's do one thing. Let's do a bit more testing. Let's change. Now I'm going to change the flow resistivity to 22, which is low medium rock wool. And then we change the material, and this actually basically gives the same results in terms of what is the panel with a better performance. But of course, compared with the previous solution, it's a bit different. But as you can see, it's the same approach. So the panel with no backing. So the panel with no air cavity behind has much worse performance than the other tools. And even if we just had like 50 millimeters behind the panel, just makes a huge difference over this area over here. So that's why I say to my clients, so if you want to do something custom made, just make sure you leave some air cavity behind the panel. And just to finish our video, I'm going to try something different. Which is I'm going to let me think. I'm going to do something. So I'm going to 50 millimeters. Okay, 50. So no, correct. So I'm going out to. So I think we've done this. So we've done the difference of we've done the changing the thickness for the same flow resistivity. We change the flow resistivity. I'm going to perhaps go back to my initial module, initial prediction for the first panel. Let me think. I'm going to put here 100 millimeters. So I'm going to use this as a starting point. Now I'm going to change the flow resistivity. So 42, like 40, 20,000, 10,000, and the orange line, it's the material with very low resistivity value. Okay, so I don't think we have done this. Yeah. Okay, so this is so basically what I get from here, from this approach over here, is that using using very high density material for with the backing behind, it's not effective unless we are dealing with a bass trap. So that's my point over here. So if we are doing with the bass trap, actually we can go back. Actually, we can go back and we can change the frequency over here. So let's change it to 200 hertz, just to see. And let's put some legend over here. So 40K, just for us to understand. Okay. So this is our prediction, but for low frequency. So this is good for bass trapping. And as you can see, if we are using a thickness of 50 millimeters with some air cavity behind, actually the best option over here would probably be the material with higher density. So go figure. So that for mid frequencies and high frequencies, that's the worst material, but for bass trapping, that's actually a good option for this configuration. Now let's say that I'm going to go backwards. Okay, and I say, okay, I want to do like a decent broadband bass trap. So I'm going to increase this for 150 millimeters of thickness material, and I have space in my room, so I'm going to put a 200 millimeter air cavity behind. Go back again here. Okay, so I'm going to change these values. Sometimes this takes some time. And now for usually I don't use Komatsu for bass trapping. I think Mickey is the best option for this kind of bass trapping, but this is very difficult to predict. Bass trapping prediction, predicting absorption for bass trapping is quite difficult. So now we have something completely different. So as you can see, now the material with higher density is underperforming in all scenarios, and it's actually us using PET material that give us the best absorption for bass trapping. So usually my starting point is first, which is the thickness of the material that I can use, which is the maximum thickness that I can use. Is it 5 centimeters, 10 centimeters, 20 centimeters? That's very important. Then I always add an air cavity behind, unless there's huge constraints in terms of spacing. And okay, if I'm talking about first reflection points, maybe I can get away with it, sort of. But for just for a controlled recording studio with linear frequency response and with very good bass trapping systems, I need to always have good thickness of my material, and also add a decent air absorption. I also use coupled with broadband bass trapping. I also use tuned bass trapping as well. Usually I use just tuned bass trapping and just attack specific frequencies in the room, or I use broadband absorption for bass traps and typical absorption panels, and then I couple a bit of tuned absorptions to correct the frequency of the room. So I hope you have enjoyed the video. This is a very complex tool to use. This kind of prediction is sometimes it's hard to do. That's why I'll always try to compare the predictions with real values measured in a laboratory. And but it's in my mind. Still, it's fantastic that we can, over the internet, we can use this kind of tools. And I have other professional tools that do the same. But I don't know why I always keep coming back to this website, because it's so easy to use and it's so straightforward that I actually love it. Okay, Thank you so much for watching, and please subscribe the video and stay tuned for further videos in the future. Thank you.